Hello and welcome to this discussion on cosmology. We'll be talking about the basic theories of the origin of the universe, the present form of the universe, and the possible future of the universe. Now, again, cosmology is really about where the universe came from, where the universe is headed, and it's one of the few aspects of astronomy that actually unites the world of the very large, that of course being the universe containing all the matter that we know of, and the world of very small. Believe it or not, particle accelerators, which attempt to reproduce some of the very early conditions in the universe, produce very high energy small particles in an attempt to understand how these particles interacted and get a better sense of what times were like early on. So sort of a twofold approach in understanding where our universe came from. We do use particle accelerators to look at the very small, and we use telescopes to look at the very large. Now, our attempt to understand the cosmos, to understand the origin of the universe, to understand what the universe is, has been going on, forever. But the real attempt to provide a mechanical model or a mechanical explanation of how the universe behaved was attempted by Sir Isaac Newton. And following his development of the universal law of gravitation, he attempted to try to understand the mechanical dynamics of the universe. He came to the conclusion that for the universe to be balanced, we have to understand that the universal law of gravitation says that everything with matter should attract one another. So in Newton's mind, if the universe were finite in size, it would have some center, and that all the matter would be attracted to the center, and that the universe would eventually collapse. This led Newton to then change his model and say that the universe could not be finite, that it couldn't have a one dominant point at the center. It had to, in fact, be infinite, and that would be the only way to balance these different forces. So, again, Newton applied what he understood about the force of gravity and used this to come up with his model of the universe. Unfortunately for Newton, however, this led to a problem, and this actually was a problem that predated Newton's analysis of the universe, and this is called Olbers' paradox, which is not actually developed by Olber. And this was first handled by Thomas Digges in 1576, and then more extensively by Johannes Kepler in 1610 and Edmund Halley, a contemporary of Newton, in 1721. And their argument was that if the universe is infinite, there should be an infinite number of stars and therefore an infinite sources of points of light. And instead of the sky appearing to be dark at night, the sky should actually appear to be light. And this would be much like looking from the inside of a forest. If you attempt to look outside, your line of vision would eventually come to a tree, and the forest being dense enough or being far enough in the middle of the forest, you'd never be able to look out. All you would see are trees. And likewise, according to this paradox, for an infinite universe, we would have to have our vision come to a star no matter where we looked at, so the entire sky should appear to be very bright. Later on, believe it or not, Edgar Allan Poe, who's better known for his poetry, proposed that the universe could be finite in size, but it also have to be finite in time, thus to avoid Olbers' paradox. And his thinking was this: well, yes, the universe could, in fact, be extensive. However, the most distant stars, we wouldn't see their light just yet, because it takes time for light to arrive to Earth, and therefore, if the universe hasn't been around forever, it wouldn't have stars forever. Therefore, what we see in the nighttime sky are just the stars that are close enough for the light to arrive to us. This is more extensively handled by William Thomson, better known as Lord Kelvin, who reached the same conclusions with a more detailed analysis. Our first really good idea of what the universe was about wasn't obtained until Edwin Hubble did his extensive study of distant galaxies. If you remember, Hubble was the one who identified the spiral nebula, or proved that these spiral nebula were actually beyond the Milky Way. And by measuring the distance to many of these different galaxies, but also the redshift of the spectra, he was able to determine their motions. And the amazing thing that he discovered was almost all the distant galaxies were moving away. Not only that, the more distant the galaxy, the faster it was moving away from us. And he developed a very important relationship that he found out that the more distant the galaxy, the faster it was moving away. And this trend was nearly linear. That if one would graph on one axis the speed at which they were moving away from us as a function of the distance the galaxy was from us, we obtained nearly a straight line or a linear relationship between these two. And that could really mean only thing in Hubble's mind, that the universe was expanding, that these galaxies weren't just moving away from us due to random motions, that their motion was a function of the universe getting bigger and bigger. Now, to obtain these measurements, Hubble looked at two very important lines in stellar spectra. These are known as the ionized calcium lines. And since most of the light from galaxies comes from stars, sort of around the mass of our own sun, G-class stars on the main sequence, K-class stars on the main sequence, maybe even A-class stars on the main sequence, these types of stars have very strong ionized calcium lines. And these calcium lines are in the violet part of the spectrum. So if we were to look at our sun spectra, we would see these dark absorption lines there. However, when we look at galaxies, all these absorption lines combine to produce, one combined spectra. You're looking at a galaxy and you put it through a spectrograph, you're looking at the light from, billions of stars. Well, galaxies very close to us would have these spectral lines pretty much set in the violet part of the spectrum where we'd expect it. Okay? Like if we look at Andromeda, we would see this. In fact, Andromeda is moving toward us, so they might be a little bit shifted. However, galaxies that were not in our local group, that were a little bit further away, would have these lines perhaps shifted to the blue. Galaxies that were really far away would have them shifted to the yellow part of the spectrum. And the most extreme galaxies would have these lines, which started all the way in the violet end of the spectrum, shifted to the other side of the spectrum in the red. And again, Hubble saw that the further these galaxies were away from us, the greater the shift, and therefore the faster that these galaxies were moving away from us. It's pretty much like doing radar. Did you ever wonder how police monitored the speed using these radar guns? They're basically microwave beams that they bounce off your car, and then you look at the frequency of the light that comes back, or the frequency of the microwaves that come back. The more shifted the microwaves, the faster you're moving. Same thing with this. It's like a radar gun for galaxies. So again, galaxies that are close to us would appear to be normal, would basically be giving off the light that we'd expect from a normal main sequence star. Galaxies a little bit further away might appear to be slightly shifted, a little bit, yellowish or orangish in color. But as they get further and further away from us, they're moving away from us faster and faster. So that light from these stars would be shifted from the middle of the visible spectrum all the way to the red end of the spectrum. In fact, you can see this in some of the Hubble Deep Field images. Stars very close to us would appear to be, I should say galaxies very close to us would appear to be, white in color. Those further away would be yellow in color. Those even further away would be red in color, all depending on the speed at which you're moving away from us. Now, Hubble interpreted this data this way. He said, imagine a loaf of raisin bread. When you first make the dough and you first put the raisins in, all the raisins are very close together, okay? But as you allow the dough to rise, the bread occupies, or the dough occupies, more volume. And the raisins, okay, although they're not moving within the dough itself, because the dough is moving, the raisins are moving further apart. So if, for instance, two raisins are very close together, okay, they'll remain pretty close together because there's not going to be a lot of expansion between them. Therefore, the speed at which they're moving away won't be very great. But two raisins that start out very far from one another will expand even greater because the distance between them is getting larger faster. Now, Hubble basically did a little thought experiment. He theorized, okay, if the universe is expanding today, it's expanding. He took the data, he could see the spectral line shifts, he could see that the distant galaxies were moving away faster. The universe is expanding. If that is true, then at one time the universe must have been smaller. Now, if we extend this far enough back in time, let's say the universe is this big in the present, and it was this big a little bit further back in time, if we keep going further and further back in time, the universe is going to get smaller and smaller and smaller, until finally it's going to get so small that it's going to occupy a point. This is like basically an explosion. Everything starts from one point and explodes outward. Now, critics of Hubble's theory called this the Big Bang theory, and this was not meant to be a compliment. It was like, well, what did the universe suddenly come from this Big Bang and we had all these stars? But basically that label, although it was a derogatory label, has stuck. And that's the label that we still use today, Big Bang. Okay, here's one of the interesting things. Again, if we go back in time, it's almost like compressing the universe. At some point, it would have been so small that the energy of the universe, we call this adiabatic compression, would have been concentrated to make the universe very hot. In fact, it would be so hot that the universe would be opaque. We call this the radiation era, when the universe was hot enough to basically make it opaque. Okay. What does this mean? We're talking about temperature for space? Well, here's the thing. The universe as it is today has expanded so far, it's about 2 degrees Kelvin above absolute zero. But if you compressed it, you'd be doing work on it, and you'd be heating it to make it hotter and hotter and hotter. Far enough back in time, it would have been so hot that it would literally have glowed. And when we talk about cosmic background radiation, we're actually talking about not the glow from the initial expansion, not the glow from the initial point coming into being, not from the universe coming into being, but we're talking about the glow back from the time when the universe was very hot, this radiation era. Here's a weird thing. When we look up into the sky, we're actually looking back in time. Now, light takes time to go from a distant object to us. So if we're looking at a star like Proxima Centauri, which is almost 5 light years away from us, or Alpha Centauri, okay? The light left that star 5 years ago. When we look at more distant stars like, say, Rigel, say it's a 100 light years from Earth. Actually, I think Rigel's like 1,000 light years from Earth. The star gave off that light 1,000 years ago, and we're seeing that light from 1 millennia ago. If we look at Andromeda is about 1 million light years from us. The light from that galaxy left that galaxy 1 million years ago. If that galaxy disappeared, we wouldn't know about it until 1 million years later. So we look up in the sky, and the more distant the object we look at, the further back in time we're looking at. Okay? Now, we believe the universe is about 13.8 billion years old. So really, if you can look far enough in the past or far enough away, you would be able to see the universe in its very early state. Okay, so it gets a little bit weird. We're looking from our galaxy, in our galaxy cluster. We look at other galaxy clusters, they're billions of light years away. The furthest galaxies we can see are about 13 billion light years from Earth. If we look at the cosmic background radiation, we're actually looking at the universe as it was when it was very hot. Okay, let's see some of the problems. Now, George Gamow realized that, again, if the Big Bang took place, again, the universe would have been very hot and dense. That's something that we already went over. If you compress something, it heats up. If you allow it to expand, it cools down. The temperature and the density would be great enough that Gamow realized nuclear fusion could take place. Now, this happens today in the middle of stars, but Gamow realized that the universe would have been so hot and so dense that fusion, lighter elements could have been fused into heavier elements. And there should be a very specific ratio of light elements due to this fusion. We call this nucleosynthesis. That if we go back in time, okay, long time ago when the universe was really, really hot, okay, and we go far enough back in time when it was about as hot as the inside of a star, nuclear fusion should have begun to take place. Hydrogen should have been fused into helium. Helium might have been fused into heavier elements. But if we go even further back in time, the universe would have been so hot, the temperatures would have been too hot for nuclei to come together. In fact, the temperatures would have been so high, nuclei would have fallen apart. So there's this really short time period which would have been available for lighter elements to be fused into heavier elements, and this would have been critical for telling us something about how the universe formed. So, what do we see in the universe? What we see in the universe is it's about 75% hydrogen. And what that means is most of the protons that formed, these are hydrogen nuclei, escaped any nucleosynthesis. They basically are left over from the original beginning of the universe and are as they were when they began. However, we do know that about 25% of all the elements are actually made out of helium. So about 25% of the elements, or 25% of the matter, 25% of the hydrogen was fused into helium during these very early moments of the universe. Some was also fused into other elements or isotopes such as deuterium. Here we see an isotope of helium-3. And a very, very small amount was converted into lithium, about 1/billionth of all nuclei. So this abundance of elements told us that, yes, the universe had to be hot at one time. Again, most of the original elements that formed were hydrogen. Okay? Some of the hydrogen was converted to helium, and then there were traces of other materials. The abundances of these isotopes closely match what would have been expected if the Big Bang happened. So this is sort of the first proof to back up Hubble's theory besides the measurements that Hubble made. And the unfortunate thing was, even though Hubble's data was very convincing, and Gamo's explanation of the isotope abundance seemed to go lockstep with what Hubble said, there's still a lot of astronomers who weren't convinced by this Big Bang theory. They subscribed to a different theory called the steady state theory, which was championed by Sir Frederick Hoyle and Hermann Bondi. And basically they said, we believe Hubble's data. We believe his observations. However, we don't agree with the explanation. In fact, Hoyle was one of those who coined the phrase Big Bang. And Hoyle's rival theory was this idea of the steady state theory. The idea was that the universe has always been around, and that new matter is constantly coming into existence as the universe continues to expand and new space is created. Hoyle, of course, didn't have an explanation of where all this stuff would come from, but it did agree with Hubble's observations. Now, let's go back to that time in the universe when the universe was very hot. Again, according to Hubble's theory, the Big Bang theory, the universe should have been very small, very compact, and extremely hot, hot enough to fuse elements. Two astrophysicists by the name of Alpha and Herman in 1948 predicted that if the universe expanded according to the Big Bang, again, it would have been very hot, and it would have by now cooled to a few degrees above absolute zero. Because all hot objects, even the universe, radiate energy according to their temperature, according to this black body radiation, we should still be able to measure this radiation. And Alpha and Herman predicted that the universe should be about 5 degrees Kelvin and thus radiate in the microwave part of the spectrum. Okay. Alpha and Herman, who were at Princeton University, were beginning to get their equipment ready to look for this microwave radiation. Unfortunately, somebody by accident discovered the radiation before they did. Correction. Two other scientists from Princeton, Dickey and P.G. Peoples, went to look for the black body radiation. Somebody scooped them on this, and these were not astrophysicists at all, but rather satellite engineers by the name of Arno Penzias and Robert Wilson. These two engineers were working on ways of bouncing microwaves off of satellites. At the time, satellites were a very new idea, and they worked for Bell Labs, which eventually became AT&T, which was very interested in developing satellite communication. And while Penzias and Wilson were testing satellite equipment right here in New Jersey at Bell Labs in Homedale, New Jersey, Penzias and Wilson kept coming across this noise. And at first, they took their microwave horn. At that time, instead of using satellite dishes, they used these large microwave horns to detect microwaves and to send microwaves. And because they were very close to New York City, they thought that, oh, maybe this noise source is coming from the city. They turned the dish away from the city and still detected it. When they looked inside the dish to see if there's something wrong with it, they noticed two nesting pigeons. They took the pigeons off, took the pigeons for a drive, but the pigeons came back and re-nested in the horn. I won't tell you what they did with the pigeons the second time, but even after the pigeons had been sent over the Rainbow Bridge, there was still noise present in their signal. Now, completely frustrated, the two contacted Princeton, and Dickey and Peebles at Princeton realized that these two engineers had discovered the exact microwave radiation that they were looking for. So with the discovery of this cosmic background radiation, with this discovery of this microwaves coming from all parts of the universe, we finally were able to get to the point where most astrophysicists, if not almost all astrophysicists, were finally convinced of this Big Bang theory that Hubble had proposed. We did still have some problems with the Big Bang theory. And unfortunately, for the scope of this course, most of these problems are very sophisticated. But I'll try to explain them the best I can. The first problem is called the horizon problem. The problem that we have is that no matter where we look in the universe, the microwave radiation is fairly even. Okay. We call this the horizon problem because if the universe expanded at a constant rate, it would have expanded too quickly for two parts of the universe to come into thermodynamic equilibrium, come to the same temperature. And therefore, some parts of the sky should be giving off more radiation because they came from hotter parts of the universe, and other parts should be giving off less radiation from cooler parts of the universe. But again, we look at the sky, and it's completely even. How is this possible? The other problem is the expansion of the universe is almost completely balanced by the gravitational force. We call this the flatness problem. And this, again, is sort of sophisticated because it has to do with general relativity and the fact that we, in general relativity, view space and time as being sort of equivalent. Okay? We look at gravity as sort of a warp in space, or a bending in space, or a curvature of space. But the problem was the universe was expanding just at the right amount to balance off any gravitational force. Sort of like if you threw a ball up in the air, gravity would pull it back down. Okay? But what if you threw the ball up in the air just enough so that it would never come down, but it would never completely escape Earth's gravity? That would sort of be the way that the universe was. How could it be this perfect? Okay? The other problem was the matter problem. The energy from the Big Bang was converted to equal parts of matter and antimatter. If you watch enough science fiction, you know when matter and antimatter combine, they annihilate one another. However, even though most of the matter and antimatter are annihilated, there's still enough matter around today for our existence. So, let's start with this horizon problem. Again, one way of looking at the universe and looking at time and space is to graph it in this sort of light cone type thing. We're right here. This is our present thing. And as we go into the future, we have the possibility of affecting all this area up here because nothing can travel faster than the speed of light. Any position here would be further away. In the past, the only thing that could have affected us would be parts of the universe where light could have traveled to us by this point in time. Again, the problem that cosmologists faced were part A and part B of the universe would never have been in physical contact with one another. Therefore, they never had the chance of interacting. But how come they were still in thermodynamic equilibrium? They had the same temperature, same energy distribution. It just seemed too perfect. Again, with general relativity, we know that gravity warps space. And that on a whole, if gravity dominated, the universe should be curved. The problem with that is, if gravity were dominant, the universe would have expanded and then quickly pulled itself back down in something we call a big crunch. We would never have had the ability to have stars form, there wouldn't have been enough time. On the other hand, if the universe expanded too quickly, we would have a negative curvature, and matter would have flown apart so quickly that it never would have had a chance of coalescing into stars. So basically, our universe formed just right, with just enough gravity and just enough kinetic energy to balance out. This just seemed too perfect. Was it a coincidence? Okay. It would be highly unlikely that the universe would be that well balanced. Again, any slight deviation, too rapid of an expansion, too much gravity, would have caused disaster for us. And where did this matter surplus come? Okay? Why was there slightly more matter than antimatter? Every time we try to create matter out of energy in the laboratory or in a particle accelerator, we always get the same amount of antimatter. Well, finally, somebody came up with an improvement to the Big Bang Theory. And although this was imperfect, it certainly went on to explain many of the problems that the Big Bang Theory had. This was done by Alan Guth in 1980. And he proposed that the universe went through some period of extreme expansion, that it increased by 10 to the 50th times. That's a 1 with 50 zeros behind it. And that this period of inflation was basically comparable to like a phase transition, like when water goes from liquid to ice or from ice to liquid. Suddenly changes many of its properties. Now, again, this inflationary period would have been very, very brief. Okay? We would have expected the universe to start out expanding and then suddenly go through this big hiccup where it went from about the size of an atom to the size of a beach ball, and then continued its normal rate of expansion. Why this was important is because it solved many of the horizon problems. Now again, according to the standard Big Bang Theory, the universe started at a point and just kept expanding at a regular rate. The problem with this is that given this expansion, it never would have been able to come into thermodynamic equilibrium. However, if the universe started much smaller, where all points were in contact with one another, and then went through this inflationary period, it would have already come to thermodynamic equilibrium. It would already have reached the same temperature, and we wouldn't have this horizon problem. We also would be able to come up with a solution to the excess matter in the universe. According to the inflationary theory, this instance of inflation would also have created a symmetry breaking where certain processes might have been preferred. Okay? In one instance, there's a particle called a kaon, which will decay either into a matter particle or an antimatter particle. We now know that there's a slight asymmetry that causes it to produce matter more often than antimatter. Again, we would expect this type of thing to occur back during the inflationary period when symmetry was broken. Now, in order to prove the inflationary theory, or at least provide empirical evidence to support it, we need to see something imprinted in the universe that was left over from the time it was no bigger than an atom. Okay? If the inflationary theory were correct, we should see some quantum fluctuations from when the universe was no bigger than an atom, still frozen into the universe today. Because basically the inflation period would have frozen in these quantum mechanical fluctuations into the matter that we see. Now, in 1991, a satellite named COBE for Cosmic Background Explorer was launched to study the cosmic background radiation. The satellite was placed into orbit because it needed to be above the water vapor in the atmosphere, which commonly absorb microwaves, and it needed to be able to view the entire sky. Now, the satellite very accurately measured the temperature of the universe to be 22.726 degrees Kelvin. Again, this is what the spectrum would look like in the microwave. It peaks somewhere around 2 millimeters. And it mapped the microwaves, and as expected, it saw a very sharp dipole structure. And this is due to the Earth's motion around the sun's motion around the Milky Way, and even the Milky Way's movement through space. It's basically a Doppler shift. But if you remove the Doppler shift, okay, here's the undoppler shifted. Here's the microwaves coming from the disk of our galaxy. If we remove all of that, we actually see quantum fluctuations, as expected, in the microwave radiation. And again, this could only be burned into the universe. If the universe were very small, about the size of an atom, then rapidly from that atom size, became a few meters across. And again, it's amazing to see that this quantum mechanical imprint, something that we normally only see on the atomic scale, can actually be seen on the universe scale. Now, after COBE, or COBE, there are other missions to study the cosmic background radiation. One of these was BOOMERANG. There were actually a few microwave studies done using weather balloons. And these stratospheric balloons would go above most of the Earth's water vapor to observe the microwaves and map out the cosmic background radiation. And BOOMERANG obtained images that were even higher resolution than COBE, and again helped confirm the geometry of the universe to be flat. More recently, we launched two successors to COBE. The first one was WMAP, and WMAP stands for the Wilkinson Microwave Anisotropy Probe. And it had the combined advantages of COBE in that it was in orbit, it could see the entire sky, and BOOMERANG with its high resolution. And after that shut down in 2010, another even more advanced satellite by the name of Planck also took measurements. Now, the result of these two missions has been very important to the study of cosmology. And by the way, COBE just orbited around Earth. Both WMAP and Planck orbited at an L2 position just behind the Earth. So it was free from the interference coming from satellite communications on Earth. Now, here's some of the interesting mission results that we had. Both WMAP and Planck's map of the sky look nearly identical. However, when analyzing their data showed some slightly different results. Well, WMAP determined the universe to be about 13.7 billion years old, with an error of about 100 million years, or 0.1 billion years. Planck placed the age a little bit older at 13.8 billion years, with an uncertainty of about 50 million years. WMAP also confirmed the expansion rate of the universe. Came up with an expansion rate of 71 kilometers per second, for every megaparsec distance of distance, and this had a margin of error of about 5%. Planck's Hubble constant was slightly lower, meaning that the universe wasn't expanding quite that quickly, at 67.4 kilometers per second per megaparsec, but both were in pretty close agreement. Both showed that the first stars in the universe probably ignited only a couple 100 million years after the Big Bang. Again, the universe is 13.8 billion years old, so stars came into existence very early on. Both came up with very similar compositions of the universe, where dark energy makes up 68.3% of all the matter in the universe. Dark matter makes up 26.8%, and normal matter, atoms, make up only about 4.9% of everything that's out there. Now, what do we mean by dark energy, dark matter? Of course, we know what normal matter is. Well, dark matter is sort of a mystery to us. It's some type of mysterious material. We know of some particles that seem to behave like the dark matter we expect. Neutrinos, for instance, interact very weakly with most matter, and therefore tend to pass through things with almost no interaction at all. And that's the way we think all dark matter behaves. However, we don't think there are enough neutrinos out there to make up all the dark matter that we're actually measuring. Therefore, other candidates include particles that we've never observed, because they are so hard to observe, called WIMPs. It's sort of an interesting name, weakly interacting massive particles. These are very massive particles that interact only through gravity, and therefore you would only be able to detect them using gravity. Another possibility are objects we call MACHOs, massive compact halo objects. These would be very low mass stars or planets that we just can't see with telescopes. But again, we think that most of the dark matter is probably contained within particles that we haven't even discovered yet, these WIMPs. Dark energy is even harder to explain. Dark energy, we believe, is currently causing the universe to expand at a faster and faster rate. And this was confirmed by measuring the distance to type 1a supernovas and also measuring the redshift. The thing is, if this acceleration continues to increase, the expansion of the universe will eventually rip everything apart. Now, let's take a brief journey in terms of what we think happened with the universe. Everybody's always asking, what happened before the Big Bang? Well, that's when time began. So, to ask that question, was there any time before the Big Bang? The answer is no. When our universe came into existence, time for our universe also began. So the clock started, if you will. So was there anything before the Big Bang? Well, that doesn't really make sense if you're asking that in terms of time. But at the very beginning, at t equals 0 seconds, everything in the universe was basically confined to a point, what we call a singularity. And from this point, everything expanded. At 10 to the negative 43 seconds, that's a decimal followed by 42 zeros and a 1. This time we call Planck time. And basically, quantum mechanics doesn't allow us to differentiate any time on a smaller scale. Okay? Basically, up to Planck's time, normal laws would not have applied for the universe. And basically, it'd be hard to explain what's going on in terms of what we know in terms of physics. Energies were well above 10 to the 23 degrees Kelvin, and the universe was basically at this unbelievably high concentration of energy. Now, a little bit later on, a fraction of a second later, was the grand unified theory era. This happened until about 10 to the negative 35 seconds. Energies were so high that all the different forces in the universe were basically identical. All the different forces in the universe would have been the same. Particle physicists believe that the unification of forces can be explained by this grand unified theory, but at this point we haven't been able to find out what that theory is. Essentially, the universe would have been filled with a hot sea of very high energy photons, leptons, which are particles like electrons, but at this energy much heavier and much more energetic, and also very massive particles we call the X boson and Higgs particles. We think we might have discovered this Higgs particle very recently in particle accelerators, but I think the jury is still out concerning that. Now, following this grand unified theory would have been inflation from 10 to the negative 35 seconds to 10 to the minus 32 seconds. This happened so rapidly and so soon after the universe formed that it's just mind-boggling when we're talking about these incredibly short times. But in a period of 10 to the negative 32 seconds, the universe increased in size by a factor of anywhere from 10 to the 30 to 10 to the 50 times. Again, during this rapid increase, there's a huge release of energy which further fueled the expansion of the universe. Basically, this provided a lot of the heat which would become the cosmic background radiation later on. After the inflationary period ended, up to about 10 to the negative 23 seconds, quarks were pretty much free to move around. Today, in our universe, quarks are basically confined to either pairs where they make up exotic particles we call mesons, or they make up other particles like baryons, which are basically protons and neutrons. Protons and neutrons each have 3 quarks, and you'll never have a single quark by itself in the universe. Again, going back in time, up until about 10 to the minus 23 seconds after the Big Bang, things were so hot that quarks could be free and could move around as they so desired. As the universe cooled further, the quarks began to condense into hadrons. This happened up to about a more manageable time period, up to about 10 to the minus 4 seconds. That's a tenth of a millisecond, or 1/10,000th of a second. And basically, matter and antimatter began to annihilate, wiping out most of the antimatter, leaving the matter that we have today. And again, this is when heavier particles like baryons began to form, protons and neutrons, which became the building blocks of atoms. In the first 1 second of our universe, it was called the lepton era. During this period, basically the universe was dominated by free protons and neutrons and lots of leptons. After this, from about 1 second to about 30 minutes, a huge thermonuclear reaction took place where some of the protons were fused into heavier isotopes, such as deuterium and helium-4. Okay? Basically, in the first 30 minutes of our universe, it was hot enough and it was dense enough that the conditions were similar to what you would find inside a star, that nuclear fusion would take place. Now, following this, the universe remained so hot for about 1 million years that it glowed with very intense black-body radiation. It wasn't until about 1 million years after the Big Bang that finally this glow went away. And again, this glow is what we see as the cosmic background radiation today. Again, when the universe cooled to a critical temperature, electrons would bind to the atoms, and matter, as we're familiar with, hydrogen and helium became the dominant matter in the universe. Again, we think the first stars formed about 200 million years ago with the first galaxies. The earlier stars are thought to be extremely massive. Because there was only hydrogen and helium in the universe, they could form and produce very massive stars, anywhere from 100 to 1,000 times more massive than the Sun. Now, the first acceleration of the universe is thought to have began somewhere around 7.5 billion years ago. That at first, after the Big Bang occurred, the universe became transparent. The expansion started slowing down. Gravity was slowing it down. However, we've noticed that the universe has recently started speeding up. And again, we believe that as the universe, the density became lower and lower, gravity became weaker and weaker because the matter was more spread out, and dark energy began to become more influential, creating this acceleration. And again, although this says now 13.5 billion years, we now know that it's 13.8 billion years. In our current time, all those quantum ripples that we see in the cosmic background radiation have also produced very interesting structures in our universe. Walls where galaxies have coalesced, and voids where we have regions that are pretty empty of any galaxies. Now, how will the universe end? That's a real strange question. We really don't know, but according to our models, we can sort of extrapolate how it would end. But really, the fate of the universe depends on if the universe is going to continue to accelerate its expansion, and what type of universe we really live in. Is it truly a flat universe? If it's a curved universe, it will begin, as it did during the Big Bang, begin to collapse, and then disappear just as it came into existence in what we call a big crunch. If we have an open or a flat universe, the universe will simply expand forever and pretty much die a cold death. Now, in any case, eventually, as the universe expands, the galaxies that we see in the sky will recede further and further from one another, and the furnaces or the nuclear cores of stars will basically die out, leaving behind remnants. Okay? Sometime about 12 trillion years from now, new star formation will completely end. Okay? In about another trillion years after that, all the stars would have run out. So all you have left over are white dwarfs, neutron stars, and black holes. We call these objects degenerate because they're basically supported not by nuclear fusion, they're dead star cores, but rather by degenerate forces within matter. After that, these degenerate cores from dead stars will begin to merge. Eventually, white dwarfs and neutron stars will slowly settle to the center of the galaxies, where they'll be consumed by supermassive black holes. Don't worry about this. It doesn't happen for another 10 to the 27 years. But if the universe is still around, it will be basically dominated by supermassive black holes. Beyond 10 to 27 years, dead stars and cold clumps and galaxies will basically merge into galactic-sized black holes. Beyond 10 to 31 years, even these galactic black holes will merge together to produce supergalactic black holes from entire clusters of galaxies. This will basically lead to what we call a dark era. Nothing will be left to produce light. Basically, everything will be black holes. Even the black holes will begin to evaporate. In 10 to the 67 years, stellar black holes evaporate due to Hawking radiation. In 10 to the 97 years, galactic black holes would evaporate. Even supergalactic black holes have a limited lifespan of 10 to the 106 years. When the black holes are basically gone, when they've evaporated, the universe will have expanded so much that all that will be left is perhaps a few particles orbiting at very large distances from one another. At this point, basically, the universe is dead. There's nothing left. A few particles here, a few particles there. The universe as we recognize it will be just basically cold, dark space. Now that seems pretty bleak for our future, but you have to remember our universe has only been around for 13.8 billion years, okay? That's billion. That's 10 to the 10 years. We're talking 10 to the 106 years before all the black holes disappear, okay? So it's a mind-boggling amount of time before everything ends. What is interesting is that recent theories about the universe, M theory, predict that our universe might not be the only one around. It's a very complicated, can't even call it a scientific theory because there really hasn't been ways of testing it properly. But according to this theory, the universe is 11-dimensional rather than 4 as predicted by Einstein. And this type of theory does allow for multiple universes, okay? And that one way that we could view things is that our universe is just one that comes into existence of many universes that are constantly being created and destroyed. But again, that's all speculation. So that's sort of an overview of cosmology. And I apologize if it seems to be very difficult to grasp. It is, incredibly complicated, or at least the theories that attempt to explain this are incredibly complicated. All right, that's it for today's chat.